Hello everyone, welcome to this lecture number 5 of NPTEL lecture on charging infrastructure. In this lecture, we will revisit the diode bridge rectifier portion. So, let us recap before starting the today's present lecture discussion. Let us recap some of the things we have discussed up till now. So, the first thing we have discussed about the EV ecosystem, where we understood that there are two voltage based battery packs which are there. That means two different levels of voltage for the EVs are present. For example, you have one low voltage batteries based powertrain, where the battery voltage goes from 48 volt somewhere around 72 volt. Then you have high voltage battery based batteries based proportional system, where the voltage goes from 350 volt to 500 volt. I mean, the battery pack voltage goes from 350 volt to 500 volt. Then after that, we have seen a building block of a DC charger comprises of DC VSC, and we have after that we have seen an AC charger, building block of AC charger, which comprises of AC VSC. So both we have seen, and we have understood what part of the charging system are present where, whether it is on board the vehicle or whether it is placed outside the vehicle. So in DC VSC case, our power conversion unit is kept outside the vehicle, that means in the EVSC itself, which means that it requires, I mean, it does the power conversion outside the vehicle, and thus it actually has a off board charger, because power conversion is taking place in the EVSC itself, so outside the vehicle. So that is why it is also sometimes called as a off board charger. In AC VSC, the power conversion is taking place inside the vehicle or on the vehicle using an onboard charger, or called as an OBC. So you require an onboard charger along with whenever you are going and charging your vehicle using an AC charger or AC VSC. While we are charging your vehicle using DC charger, you are having DC VSC, where the entire power conversion is taking place inside the EVSC itself. You are just plugging in the DC voltage into your vehicle. Then after that, we have seen different types of charger which are there in the ecosystem. Like we have seen different modes of charging. We have also seen different charger plugs which are used, charger plugs or vehicle inlet connectors which are used in different parts of the world. We have seen that as well. And then after that, we have seen different levels of charging as well, we have seen briefly. So we understood what all things are available in this EV ecosystem, and we also understood some of the important jargons or some of the important terminologies which are present in this EV charging systems or associated with this EV charging system. Now let us move ahead and understand the different aspect of power conversion unit. So as I mentioned, the power conversion unit consists of an AC DC converter, input AC, output DC, followed by isolated DC DC converter, which gives a controlled DC at its output. Now depending upon whether it is an AC charger or DC charger, this will be either placed onto the vehicle or it will be placed outside the vehicle. So we will discuss both scenarios, and we will see one by one different AC-DC converters and try to understand different aspect of those converters. Before starting that, let us see some of the need, I mean why we need an AC-DC converter, or what does an AC-DC converter do and why it is being used in the power conversion unit. So, let us write AC-DC converter requirements or needs, you can say. So, why we need an AC-DC converter? We need a AC-DC converter because of the first thing, obviously conversion from AC voltage source to DC, and while doing the conversion you want to have the controlled, or you can say regulated DC output voltage, and again along with having the regulated DC output voltage, irrespective of whatever be the load, you also want that the level of voltage can also be controlled. That means, let us say if you are putting, I want to go for 450 volts, so at a desired level the voltage can be controlled. So, the control and regulated DC output voltage at desired level, maybe that could be a much simpler way of writing, at the desired level. Then the third requirement, okay, so one requirement is done, that we are converting AC to DC, and then we are also regulating the DC at its output irrespective of load, whatever they are seeing, that means irrespective of the charging stages in which the battery is. So, irrespective of that, you could be in a position to control the DC output voltage, and that too at its desired level, I mean what level you want it to keep. So, that has to be defined. Then after that, these two things are the primary objective. Now, along doing this, you also want, while doing this, the current drawn from the source must have an unity power factor. That means you are converting an AC voltage into a DC voltage, along doing those AC conversion from AC to DC and feeding it to the load, you are making sure that the which you are drawing from the source is having a unity power factor. Now, why you need a unity power factor current? Obviously, you do not want to have any reactive component to be flowing in your circuit, as well as you wanted to actually transfer the entire real power to the load without having the reactive power to flow within the circuit. So, and thus it will also help in reducing the sizing, reducing the component sizing of your power converter. That means the RMS currents in the power converter you may require less in the power devices. So, you also want, along with unity power factor current drawn, you also want that the current must be, the current drawn must be having a sinusoidal variation, or if not nearly sinusoidal variation, or nearly sinusoidal variation. So, along with unity power factor current drawn, you also want the current drawn to be closer to the sinusoidal variation. That means if you have a sine AC source, you also want that the current drawn should also be following the voltage. So, current drawn must be having a sinusoidal variation, and along with doing this you also want that harmonic content should be less. That means if you have the harmonic content to be less, means TSD of current drawn or the TSD is less. So, these are the things which AC to DC power converter need to do. First, obviously it converts the AC voltage source to the DC voltage and then feeding it to the load, and along with doing that you also want that the DC output voltage which you are obtaining must be at a desired level, and that too it must be a controlled or regulated in nature, and the current drawn from the source must be having a unity power factor. That means the voltage and current are in the same phase, there is no phase lag or phase lead in the current and the voltage, and the current which is drawn from the source must be having an sinusoidal variation, and along with that the harmonic content in the current which is been drawn from the source must be less, that means the TSD must be less. So, this will help in making sure that you are drawing a sinusoidal current and you are making sure you have a unity power factor. That is when you can have the more efficient power conversion, and at the same time you are also not creating problems in the grid. That means you are not injecting harmonics into the grid, or your grid is also not get polluted because of the connection of the EV charger. So, these are the some of the requirement, and let us see, let us revisit or let us see what all converters we can have which can follow this particular requirements and can be used and then can be qualified to be AC to DC converter unit of an power conversion unit of an EV charger. So, let us see the first AC to DC converter, which is a very simplest converter, which is the diode bridge rectifier. Now, before starting that, let me also discuss one thing. If you have a charger having a single phase input, then one need to have the single phase AC to DC converter, and if three phase AC input is been given, then one require three phase AC to DC converter. So, let us focus our discussion on a single phase AC to DC converter, and the simplest form of AC to DC converter is nothing but single phase diode bridge rectifier, which is also called as the uncontrolled rectifier. We will discuss this, like why it is called uncontrolled rectifier. And in this single phase diode bridge rectifier, we have two kinds of rectifier. We have first one, which is half bridge rectifier, and the second one, which is the full bridge rectifier. So, let us discuss single phase half bridge rectifier with resistive load. Let us revisit its circuit. It looks like we have a single phase voltage source and it is been fed to a resistive load via a single diode D. Let us define our resistive load as RL and diode as D, and our voltage source is Vs, which is equal to Vs peak sin omega t. it is varying sinusoidally with time. So, it is Vs as a function of time. Now, if you consider this particular circuit, in this the diode D turns on when the Vs of T, or I mean interchangeably I will be writing small Vs, when the Vs is in the positive half cycle. Why? Because if it is having a positive half cycle, this anode of this diode will be having the positive polarity of voltage, and thus it will be forward bias, while in the negative half cycle the anode will be at the negative polarity of voltage, and that is why it will be reverse bias. So, it turns on when the Vs is in positive half cycle, and it will allow the current to flow through it in the direction from anode to cathode. This is its anode, this is its cathode. Now, and so this is the, it turns on, or you can say forward biased when the Vs is in positive half cycle, and it is reverse bias when Vs is in the negative half cycle. Let me draw the circuit here. RL D Vs Vs peak sin omega t. Now let us see how the waveform look like. Since we have a sinusoidal voltage source, let me draw the sinusoidal voltage. So, let me draw the sinusoidal voltage. Okay. Now, accordingly, you also have different time stamp. This is your Vs, and this point is nothing but Vs peak of the sine wave, and this is your minus Vs peak. It goes from this one, that means the distance from here to here is Vs peak. And let us also define one term which is a T, which is nothing but the time period between the starting of the cycle and the ending of the cycle. And so, if this is the Vs, so in positive half cycle, this particular positive half cycle, this anode of this diode sees the positive polarity of voltage, and as a result of which it will get forward bias and thus allow the current to flow through it. And also let us define this voltage across this as Vd. So, since the diode is on in this positive half cycle, your Vd will be equal to the Vs. Assume is an ideal diode, that means the forward voltage of the diode is 0. So, since you are applying a positive half cycle voltage from its input, the anode of this diode, and I mean it will be at a higher potential as that of cathode, and as a result of which diode gets forward bias. Since the diode gets forward bias, what you will see is that you have a voltage Vd which will be following the same thing which was there with Vs. So, this is also following the same pattern which your Vs or voltage source is following. So, we can say that this Vd is equals to Vs when Vs is greater than 0 and it is 0 when Vs is less than 0. Why we are writing? Because when the Vs is in negative half cycle, the anode of this diode is at negative potential. That is when it gets reverse bias, and that is when it does not allow the current to flow through it, and the entire voltage will be dropping across this diode itself. Since we have drawn the Vd, let me also draw the diode voltage, or more specifically the anode to cathode voltage across the diode. Since during this time the diode is forward bias, thus the voltage across diode is nearly 0, as we assume that our forward voltage is 0. So, our voltage across the diode is 0, and during this point our diode will be blocking or will be seeing the negative potential across it, and that is when negative voltage across it, that is when it will, if we define this thing. So, the voltage across the diode will be of the same shape as that of the Vs, and then again it goes to 0. So, and at this point is nothing but our Vs peak. So, in this particular case we have seen that during this period of time, during the positive Vs, our diode is conducting, and that is when the voltage will start appearing across the load, and that is when the current will be drawn from the source, and in the negative half cycle the diode will be reverse bias and the entire voltage will be blocking across this diode as drawn here. Now, let us also draw the current. So, let me draw the current with the other color. So, since the voltage is in this shape, which is the half sine wave shape appearing across the resistive load, so current will also be following the voltage, and they have the same shape as that of voltage, where this peak will be nothing but Vs peak by RL. And if you take this peak, which is nothing but your Vs peak, while during this instance, during this time period, this current is nearly 0, and then in this particular place again it will come back and having the same with the peak same as that of previous peak, which is Vs by RL. So, with this we can see that the current supply to the load is only happening in the, or the power supply to the load is only happening in the only the positive half cycle, that means just the T by 2 period, while in rest of the T by 2 period the circuit, I mean there is no power which is been delivered to the load. Now, since our voltage is of the shape of the half sine, I mean half sine wave and then 0 and then again the half sine wave. So, let us see what is the average voltage of average output voltage. So, the average value of Vd, which you can say that Vd average, which is also you can say that the voltage applied across the load is nothing but, if you do a simple calculation, so the thing will be 1 by T. Since we are taking the average, it goes from this, because the waveform repeats itself after the duration time T. So, you have 1 by T going from 0 to T by 2, 0 to T by 2, it is nothing but your Vs peak sin omega t dt, plus you have a 0 voltage here. So, you will have the 0, I mean 0, the remaining portion of the equation will become 0. So, we will have this particular thing, and then when you solve this particular thing you will get omega t minus cos omega t going from 0 to T by 2, and that will give you Vs peak by omega t cos omega t by 2 minus cos 0. Again, from where, I mean, if you see the omega value, omega is nothing but 2 pi fs, where fs is the supply frequency and the t value is nothing but 1 by fs. So that implies the omega t is nothing but equal to 2 pi. The same thing we will put over here, v as peak, omega t we can put as 2 pi minus of cos pi minus cos 0. This will be v as peak by 2 pi minus 1 minus 1, and that will be your v as peak by pi. So this will be your VD average, which will be applied across the load RL, and accordingly the current will be drawn from the source, or current will be drawn by the load. So this is what we have seen, the average voltage. Now average voltage will be somewhere, if I draw the average voltage, so average voltage will be somewhere here, that line which is given as VD average. Now let us see what will be my current drawn from the source. Now if I draw again a circuit, then the current drawn from the source, let us say Is, is nothing but equal to Id, which we have drawn, your Id, the current, and the same current. So this particular, the red color thing is the current, which is nothing but your Id, so which is going into the load Id, and here you have Is. Similarly here we can Is, and current going into the load is Id. So we can write that my Is current, which is been drawn from the source, is nothing but Id when Vs is greater than 0, and 0 when Vs is less than 0. Now if you see this particular circuit, in this particular circuit you have a load which is again depend, because you are supplying that particular load. So it is the external thing which has been placed, and you have the input source which is not the part of the power conversion unit. Now only thing which is there is the diode. So now let us see the diode selection, how we can do this diode selection. In doing the diode selection, depending upon the parameters of the circuit, we have primarily two things, which is the voltages and the current. So this, we have the voltage ratings of the diode, and in that voltage ratings what we have is, we have several types of voltage rating which has been defined for the diode. Now the first voltage rating is your peak repetitive reverse voltage, which means how much maximum voltage it can withstand, or it can block, and that too when that peak will be in the repetitive form. And along with that you also have peak reverse voltage. Sometimes in the data sheet it is been given. The peak reverse voltage tells what is the maximum voltage it can block when it is reverse bias. It is the once, I mean in one time, how much peak, maximum peak voltage it can withstand. And then you have the reverse voltage, another rating which is defined as a reverse voltage, or it is also called as a DC blocking voltage, which indicate what is the maximum DC voltage it can block. Now if we see, if we try to understand what is the peak repetitive reverse voltage, if we see, let's say the cathode to anode voltage across the diode, I mean the reverse voltage across the diode has shape which is repetitive in nature. So the this particular point is nothing but your peak repetitive reverse voltage, which is also defined as a VRRM. VRRM. While whenever it has to block a DC voltage, then this maximum DC voltage it can block. This is the your reverse voltage or DC blocking voltage, and this is the VRDC, the maximum DC voltage it can block. So these are the two things which is there, which is been given in the diode data sheets. Some voltages are given, sometimes some are not given. So the designer has to take a well judgment what voltage to be taken while defining the, or while choosing the diode. If, let's say if it is used for the rectifier application, or the application where it is a I mean where we have the repetitive on, I mean forward bias and reverse biasing of diode, then maybe peak repetitive reverse voltage is the best possible thing one can, I mean is the best thing to be seen. While when the diode has to just block a DC voltage, that's when they can see the reverse voltage or the DC blocking voltage. Similarly, you also have the current ratings of the diode. Different current ratings of this diode are there. In that you have first one, which is average forward current. This average forward current is again the average value of the current going through this, through the diode when it is forward bias. Then it has the, sometimes you also have average rectified forward current and average rectified forward current. Sometimes in some of the diode datasheet this has been given. However, most of the time this is average forward current, and sometimes it is also called as a continuous forward current as well. Then you have another rating which is again repetitive peak forward current, given as IFRM, and some it is also given also there is one more rating given, non repetitive peak forward current, as IFSM. Generally, while defining these two things, they will also mention the time period of the pulse current which is being or the time period for which this current can be applied, that maximum current can be applied. So they will also mention that in the data sheet while defining these parameters. And along with this, there is another rating which is been defined, which is called as the I square T rating. This I square T rating is actually used to select the appropriate fuse rating, because fuse also have this I square T rating. So accordingly, the fuse, depending upon this I square T rating, the fuse can be selected while this diode will be used in the circuit. So for protection, the fuse can be selected. So that's why this I square T rating will be defined, where this I is nothing but the RMS value of forward current, or when the diode is forward biased, and you can say that T is the time period of the pulse, or you can say that for which the current is allowed to flow through the diode. So, this is again one rating, one particular rating for the safe operation of the diode which has been defined. Now, if we consider, if we try to design our this single phase half bridge diode rectifier. So, in this particular thing, if we see the diode selection criteria, now if we talk about voltage rating, in voltage rating, if we talk about peak repetitive reverse voltage, or you can say that VRRM is nothing but, if you look carefully in our waveform, the peak value this diode will block is nothing but Vs peak value, which is the peak value of your input AC voltage. And if we try to see the average forward current is nothing but the average voltage across the load which we have derived Vs peak by pi divided by resistance of the load, which is value of the resistive load, which is the RL. Similarly, one can also calculate the RMS current which is going through the diode, which is nothing but can calculate as 1 by T, because this diode conducts from 0 to T by 2 and it will be 0 and then again it will start conducting. So, this conduction of the diode repeats after the time T. That is why we are taking the mean for the entire fundamental cycle or for the entire line cycle, and it is going from 0 to T by 2, because in the positive cycle only there is a current, while in the negative cycle there is no current. That is why they are going from 0 to T by 2. You can write Vs peak sin omega t divided by RL is the current square and the integration under dt. Now, if we solve this particular integration, one could easily get this particular integration. While solving, one could get a value nothing but Vs peak by 2 RL. So, this is the RMS value using which I square T rating can be found. This is the average value of the diode one can select depending upon the value of the load it is supplying, and the voltage rating one can select using these three ratings of, these three ratings, appropriate diode can be selected. However, these are the ratings which I mentioned over here are the rating which is determined by the circuit in which it is being operated. However, there are other ratings also like forward voltage drop of a diode and also the dynamic resistance. Those things also could be considered, but depending upon the current and the voltage rating of the diode, one can select the family of diodes, and then from the family of diode one can select the most appropriate diode, and that is when this particular converter can be designed and can be used to supply load from the AC source. This AC source will be converted into a DC and that will be supplied to the resistive load. So, in this way one can select the required diode, and that is when one can obtain the single phase diode bridge rectifier which can supply the load from an AC source by converting that AC into a DC and supply it to a load required, supplying it to a resistive load. Thank you for patiently listening to this lecture. In the subsequent lectures, we will see the full bridge configuration of uncontrolled rectifier, and we will take some of the references from these two diode bridge configurations, and accordingly we will logically navigate and reach to the circuit which are being used among different EV chargers. Thank you.